We're talking about the counting methods and permutations today, and that's really today, and tomorrow we get into the real number system. But for today, spending time on this, you're going to get a lot of information about probability that's going to come around to you. So what I want you to do is I want you to read through this. It's the same sheet that you've got right now. It should be on its way, Quaid. I see you. Okay, so you got that. I want you to read through it and talk to your neighbors about what a tree diagram is, please. Okay, so talking about Jim and her mom going to an ice cream shop, as all good mother-daughter pairs do, they start talking about the ice cream and they start breaking out into a tree diagram here. Okay, she can get chocolate, fudge, strawberry, or chocolate, strawberry, fudge, or vanilla. She can get cake or waffle cone or sugar cone. She can also choose whether or not to have it dipped in chocolate. Use tree diagram to show how many different possibilities. Now, if we're going through this process of a tree diagram, some teachers are a little more picky than others. I've seen some teachers that expect you to start your tree diagram out here at like a seed, okay, and your tree grows from that seed. I don't get that picky. I do expect, though, that when you're going through your tree diagram, that you think about your labels ahead of time. So they go to an ice cream shop. She can get different types of ice cream. So I'm thinking of this as an ice cream section here. Okay, and then from that ice cream, and I'll zoom in there a bit. Okay, from that ice cream, we know that she can get the chocolate. So we come up with an abbreviation for chocolate, maybe C. She can have strawberry. I'm guessing S would be fine. And it's nice to spread this stuff out so you have room. So maybe give yourself a little room because your trees gets quite big there. And then from strawberry, she could also have, or other ice cream could be fudge, and it could be vanilla. Those are different types. Okay? And then from that, we know that the next option she has is a cake, waffle, or sugar cone. So the type of cone. Okay? Again, it's cake. Maybe you go C case because you've already used C. Waffle and sugar. And notice, if I choose to get chocolate ice cream, I could have chocolate ice cream in a cake cone, chocolate ice cream in a waffle cone, or chocolate ice cream in a sugar cone. So there are three different options from that one chocolate type. Okay? And so with my strawberry, I could also have it in a cake, a waffle, or a sugar. Howdy. You might have. You can go check. Yeah, go for it. So once again, strawberry could have any of those three options. Same thing here. I could have it fudge in a cake. Did you? All right. Yeah. A waffle and a sugar cone. Okay. And then finally, I could have vanilla in a cake, a waffle, or a sugar cone. Now, how many would choose a cake cone? Just out of curiosity.
It's like the little baby ones.
Okay, how many would choose a waffle cone? I'm going with waffle myself.
With a bowl.
Sugar cone?
Sugar cone for the weird kids.
This one.
He's one of us lame. Choose the bowl.
Okay.
Yeah, he's one of those people who like to use soda.
Sorry for getting us distracted. I knew everyone was wondering. So you can also then have it dipped or not. And the title there I'm just going to use is dipped, question mark. Okay? And then my question mark, it's either yes or no. So if I choose chocolate in a cake cone, it could be dipped. It might not be dipped. So once again, yes, no. In a waffle cone, could be, maybe not. And then yes, no. Sugar. Now this is why you should really spread things out, right? Because notice how cramped my stuff's starting to get. So I've got all my cake, or my chocolate, options above that line. So yeah, I have strawberry in a cake, dipped or not. Strawberry in a waffle, dipped or not. Strawberry in a sugar, dipped or not. So I've got to do that yes, no thing. It gives me a bunch of branches there. Now some people like to put their tree diagrams that way. They like to have it go down. Vogel, for instance, likes to do that. So if you were in Vogel's class, you would do that. So you may have classmates, within your grade level that are doing it a different way. And it's just, that's the way Vogel ends up teaching it. It's not right or wrong. It's just, it's up to you how you feel more comfortable doing it. Okay? So once again, you just keep with our yes, no's. Becomes kind of a tedious process. All right, so you got to be thinking there's got to be an easier way to do that, but at least there's your tree diagram, and the benefit of a tree diagram is at the end you end up with what's called a sample set. And that sample set is all of your possible choices. Oh, one last thing. If you had that teacher that really wanted you to go from the seed, there it is.
I did that.
Now you have it. Okay, and that's fine. I just never got too picky about
It
that.
looks
There.
more like a tree.
Yeah, that's right. There it is.
It
Okay.
looks like a tent.
So now you can feel better about it.
Can we call it the tent diagram?
No. Okay. So what we're going to do from there is we're going to list our sample set out. Hey, eyes and ears right here. Tyler, go ahead.
Oh, how you do it?
Yep.
You do C, comma, CK, comma, Y, C, comma, CK, comma, N, C, comma, Y,
Oh,
C,
God.
Hey, now is he correct? Yep, he's correct.
It's just really tedious. Out of
Oops,
three,
no longer
Out
CK.
of 3 flavors, you have 24
So
options.
so we have C, W, and Y. You don't have to put the commas. That'll save you a little time. C, W, N. Hey, C, W, N. All right? C, S, Y,
What is that?
and C, S, N. Okay? S, C, K, Y, S, C, K, N, S, W, Y, S, W, N, S, S, Y, S, S, N. Who ain't got no time for this? Oh, ain't.
Ain't nobody got time
Man,
for that.
ain't that cool. F, C, K, Y, ooh. F, C, K, N.
Can we move on, please?
Hey, now part of the reason I'm going through this is I'm assuming you know a sample set. That's one thing. I'm also assuming that you can do this. Some of you have never done this, and you're like, I'm not going to write all that junk out that McCoy's doing. Look at him. He knows how to do this, and he's even writing it out. What a waste of his time. I agree, except for I'm teaching you, so it's not really a waste of my time. Okay? And when you take your test coming up on Thursday, you'll be expected to do a tree diagram and list the sample space. Just for fun.
Wait, for fun?
Yes.
Wait, so that means it's not graded?
Yeah, and that'll be fun too. Trust me, I love grading. I sit there with my coffee and my chihuahuas and grade.
You have chihuahuas?
My Labrador. All right.
I don't like
So,
dogs, but they're beautiful.
you would love my dogs. Okay. With that being said, how many options do I have here?
6.
6.
Toy,
And?
cheese,
6 and
6.
Okay. So a grand total of
24.
24. 24 total options from that tree diagram.
Wow.
What are the benefits of a tree diagram? Tyler?
verbally see everything that's going on. You can look at all of these.
Verbally?
Visually, yes. You can visually see it. You can visually see what you said verbally.
See words?
Yeah. Okay. Very good. Now, with that, any questions? Now you have your example. What I would like you to do is take a look at, oops, let me zoom out here. Okay, still same thing. Let's go ahead and take a look at this. We're going to define factorial, which you're going to need. Okay, so factorial calculates the number of ways a set of items can be arranged. Okay? factorial, number of ways a set of items can be arranged. And after you get that into your notes, go ahead and copy down this example underneath it. We will call it 8 factorial. That's this symbol right here means factorial. I know it's an exclamation point, yes. But it means in math, factorial. So those of you that you get all excited about your assignment, you're like, my answer is 8. Yeah. Okay? Well, really, you didn't put 8, yeah. You put 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
Oh, that's nice.
You put the wrong answer, in other words. All right? Factorial means 8 times 7. Well, this 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, there's a very compact way of writing that. We write it as 8 factorial. So those of you get all happy, happy, joy, joy about your answers, and you put exclamation points, you're putting the wrong answer, dude.
Wait, so
Yeah, I do, because now you know.
so if we
Well,
do
yeah, but you didn't do that before we did it.
Well, now you do.
so if we did like 99 and an exclamation point.
Yeah, 99 times 98 times 97. Okay, I need everyone to get a book and a graphing calculator. So in your textbook, page 38, graphing calculators. Now, mathematically, I expect everyone should be able to multiply this out. Maybe not in your head. We can go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and get?
40,320.
Okay. Now, there is a quick way to do that. You can actually use the factorial key.
What?
Okay? So if you use 8 and then go to math and then over to PRB. So those of you that are taking, once again, if you're taking notes on this, I would hope that somewhere in your graphing or in your binder you have a graphing calculator section, not just on your normal note page. Because when we do this again, when we start talking about combinations later in the year, and I'm going to say, okay, use the factorial key, and you're going to be like, I don't know where that is. Maybe I'll look back to my notes, and you won't know where these notes are. You won't remember the section. But if you have a graphing calculator section of your binder, it makes it easier. But anyway, it's math. That's the button. And then you arrow over to the right. Actually, you could go to the left once, I guess. If you go to the left once, it takes you to PRB. Okay? And then option 4 on my calculator. That might be different on some of yours, but there's my factorial. Okay? So if I want that and I just enter it, there I have to put the 8 first and then the factorial and hit enter, and then it gives me my answer.
That's cool.
Yeah, I don't like to brag about it. It's pretty cool, though.
That's really
Okay?
cool.
It is really cool. Not Rose by Collins, but it is cool. Okay.
You don't have a saying for this one too?
No.
Yay.
In fact, I don't. Okay? In fact, tutorial, I don't. Fine. All right. Any questions there? Okay, next step. I want you to explain what the fundamental counting principle is in your own words. Sorry, not the fundamental. You'll hear it as fundamental counting principle sometimes, but multiplication counting principle. It's in your book on page 38. Explain what it is in your own words. Maybe. All right, so what is the multiplication counting principle? Cool.
It's like the way that you figure out how many different ways there are to make a selection.
Okay, the way to figure out how many different ways there are to make a selection. Okay. Anything to add?
Basically, it's basically breaking down the elements of the tree thing into an equation.
Okay.
And what you do is each number represents the amount of numbers there are in each group, kind of thing, and you multiply that out.
All right, so it's a way to break your tree diagram down into an equation.
Yes.
Okay.
Thank you.
Alyssa?
The number of ways of one solution times the number of ways of another solution.
Okay, so maybe one set times another set. So if we stick with this tree diagram, rather than having to go through this process, if we know there are 4 different choices of ice cream, and there are 3 different choices of cone, and two different choices of dipped,
Yes.
the fundamental or the multiplication counting principle says you can multiply those options together to get the total number of choices.
That would be a factorial too, wouldn't it?
4 times 3 times 2. It's a portion of a factorial.
Yes.
Okay? Well, I mean, if you put a 1 in there, it is a factorial if you finish it off with the 1.
Yeah.
That's
Okay?
crazy.
Now, why don't we have the 1 there? Does it mean anything?
No.
No. So, yeah, we have another way to think of it. This is 4 factorial. Okay?
Sweet.
All right. Hey, we got the fundamental or the multiplication counting principle. Okay. So it takes the number of choices you have and you multiply those together to get your total number of sets available once you've combined all those choices. Using a tree diagram was our visual. Okay. So what I want to do now is I want to take our permutation, talk about permutations. All right? On a permutation, this is going to take and it's going to break up our factorial now. So we went from, let's recap real quick. We went from the picture to kind of a shortcut method, right, without having to use the picture. And now we're going to use factorials in what's called a permutation. Okay, I want you to define what a permutation is, please. Define permutation.
Wait, how are we?
Now you can define it as, what is a permutation? Hannah?
An arrangement of items in a particular order.
Good, an arrangement of items in a particular order. All right, so it's different than what we just did, where we just took all of our items and we tried to figure out how many different choices we have. Now we're going to take items and put in a particular order, which is what a permutation is. Okay, so before we do that, we need to have some background on that. So what I want you to do is, if you didn't write this down, complete the following statement. The number of permutation in items of a set arranged R items at a time is, now when those, how many of you copied that down when you defined permutation?
No.
Oh, all right. Where's permutation?
Up here, it's not there.
Okay, well then let's pause on that. Let's not do that yet, if you haven't defined that yet. Why don't you look at the top of page 40 and answer questions 2 and 3. Okay? Work with your groupies there. I did hear some of you, had about 3 of you ask me, to actually said, hey, that's not a permutation, right? Because it doesn't go out to 1. Or why doesn't it go out to 1? Okay, well, sometimes we don't need it to go out to 1. Okay, so when I multiply this out, what do we get?
19,958,400.
Wow.
Right there? How many got that?
Yeah.
Yeah.
Okay, what happened when you did this? Okay, same thing.
It's just simplified.
It is simplified, yeah. All right, so really what they're doing, no, here, 12 factorial. If I wanted this 12 factorial, I would actually have to write out 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, there's 12 factorial. We have 12 factorial. Divided by 4 factorial. Well, 4 factorial is just,
4 times 2, 3 times 2.
it's 4 times 3 times 2 times 1. Now, when you're dividing, note there aren't addition signs or subtraction signs, it's multiplication. When you're dividing, you can cancel these things out. Okay, so when I divide 12 factorial by 4 factorial, really what I'm doing is I'm getting rid of that last chunk, which leaves me with this part right here. That's why they're equal. Everyone see that?
Yes.
So 12 factorial divided by 4 factorial is really, it's really 12 factorial without the 4 factorial at the end. So sometimes you'll see that actually marked down as 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. You would see that in a book sometimes, and then divided by 4 factorial. Those two pieces cancel. Okay, now why do we do that? Why am I going through that? Because when I'm writing fractions to express factorials using permutations and combinations, we use a formula, and it really does stuff like this. So before we can do that, I want to make sure that we have that down. Write a fraction with factorials to express this. So first of all, this piece right here, that piece right there is like having 15 factorial, correct? Except for what part are we missing?
11.
We're missing the 11 factorial at the end. Okay, we're missing the 11 times 10 times 9 times blah, blah, blah. So that's the fraction form of that. Okay? All right. As Jaden pointed out, this is the simplified form. Okay? And we could verify our work by multiplying it out. Any questions there? Okay, well, let's talk about this then. I want you to look at permutations. You can write the number of permutations of 7 items arranged 3 items at a time as 7p3. This relationship between permutations and factorials can be summarized with this formula. Now, before we get to this mess down here, let's understand what a permutation is asking. A permutation says, hey, you have all of these items. Okay? Our goal is to take those items and put them in an arrangement. All right? So we're taking 7 items and we're arranging 3 items at a time. Okay, so we're picking out of 7 items, we're picking 3 of them. So 7, pick 3. All right, that's a permutation. Now later in the year we're going to talk about combinations, but for now it's 7p3. Eventually you're going to see what's called 7c3. Okay? But let's get this down. This formula. The number of permutations of n items of a set arranged r at a time is npr. N permutation r. That is the formula right there. Ignore this piece just for a minute. Just copy down this chunk. All right? Hopefully this will become more clear with the example we're about to do, because it's more real life. But this part right here just says P or NPR equals n factorial, so whatever that number is, over n minus r factorial. And this says for r being less than or greater than or equal to 1. In other words, r can't be 0. Okay? And n has to be bigger than r. So this number has to be bigger than that so we don't get a negative. So you can't get a negative or a 0 in this factorial down here. Okay? All right, that's for our permutation. Now, this is what it would look like in an example. 7p3. So we put the 7 here. We go 7 minus 3, or that minus that, to get 7 factorial over 4 factorial. And this is why we just did what we did with factorials. Because hopefully you recognize 7 factorial minus 4 factorial, for those of you still paying attention, is 7 times 5, or 7 times 6 times 5 times 4 factorial all over 4 factorial. These two pieces cancel. So really, 7 factorial over 4 factorial, or 7p3, is 7 times 6 times 5, which is 210. Okay? Once again, this is a compact way of showing that. Okay, maybe not understanding what permutations completely mean, which I hope you'll know here in a minute. How many understand the math behind it? Okay. All right, let's see if we can make the actual permutation piece, like what we're actually finding there when we're using permutations, more relevant to you. Okay, 4a. This is on page 41. So suppose you want to arrange 6 trophies on a shelf. And like all good teenagers, you want to figure out how many different arrangements you can make. All right? So selecting from a collection of 15 trophies. So you have all these trophies. Your mom or dad or whoever said you can only put 6 of them on a shelf. And then you're looking, okay, I've got 15 trophies here. I've got to pick 6 of those. So once you pick those 6, you're like, okay, these are my 6 favorite. These are my others over here. So I've got my 6 favorite trophies. Okay? So you got your 6 favorite. And maybe they're boring trophies. They're just a bunch of letters. Okay? Those 6 trophies and their letters. So you picked your 6 favorite trophies. Once you pick them, which is the first part of a permutation, you have to choose your 6. That's actually called a combination, which we study later. Once you get them, then you go, oh, well, should I put A first? Or hold on, should I put B first? Hold on, maybe you should put C first. Oh, no, hold on, let me put D first. So then you start putting them all in these random orders, and you sit in your room for hours reordering your trophies. You're like, okay, I got the perfect order. Yes. Okay? That is a permutation. When you pick out of the 15, you've picked your favorite 6, and then you figure out what order you want them in. So there's a lot right there. All right? So think of it this way. If I had 6 positions on my shelf, out of those 6 positions, if I have 15 trophies, how many different trophies could go in my first position? 15 of them. How many are left to choose for your second one? And your third? And your fourth? And oh, we're out. We're out of room. Well, this really, what you've done here is almost 15 factorial. What piece have you left out?
9 factorial.
You left out your 9 factorial. Yeah, which really we know as, this piece is gone here, really we know this as 15 factorial over 9 factorial, right? That gets rid of that piece right there, that divided by 9 factorial. And this thing right here, we also know as 15p6. Right? We subtract 15 from, or 6 from 15, and that gives us that thing. Lee?
So up on the last one, explain what is down there formula for 15p6 should be 15 minus 6. 15 minus 6 factorial would be 9 factorial, and that's not right according to that.
Explain why the denominator in the formula should be this. Yeah, it should be 9 factorial, right? 15 minus 6 is 9 factorial. Yeah, and the reason the denominator should be 9 factorial is because that's the part we left out of the top, is that 9. So that's what we're dividing by there. Okay, so the formula is this. It makes this, right, when we actually use our factorial. Remember, what our formula was n factorial over n minus r factorial. Well, n is 15 and r is 6. So we subtract those two and that becomes our bottom, that's our top. Okay? How many think you're with me? Okay, now we're going to find out here in a minute. Now I didn't figure out the answer there, and I'm not so concerned about that yet. But what I want to do is take a look at our assignment. And while I'm doing that, I want you to drop back to the very first thing we did today. I don't want you, other than making a tree diagram, I want you to figure out the answer to that using the multiplication counting principle or permutations, whichever you think we should. Am I using permutations or fundamental counting principle or multiplication counting principle? Yeah, here we're just using multiplication counting principle. A sandwich shop offers 3 types of bread, 4 different types of meats, 7 types of toppings. How many different sandwiches? So 3 times 4 times 7. Or a grand total of?
84.
84 different
Sandwiches.
Okay? Now, the difficult thing for you today is going to be to figure out when to use what. When should I use tree diagrams? When should I use multiplication counting principle? When should I use permutations? Let's take a look at this real quick. This is your assignment. I want to look at number 1, number 5, and number 9 on the example side. 1, 5, and 9. Number 1, suppose you plant an oak, hickory, dogwood. Okay. Number 5, in how many different ways can you line up 10 people to go into a show? And number 9, and 28 projects being judged Top 5 projects will receive awards. How many different ways can the awards be given? I want you to figure out how you're going to solve those 3 different problems. And please remember, when you're doing this, you've been giving a couple of different ways today. You have factorials. Well, let's start at the beginning. You actually have fundamental counting principle or multiplication counting principle, factorials, and you have permutations and tree diagram. But you're not going to. I hope you don't have to use tree diagram on any of these. Okay? Talk about it. You get about 2-3 minutes to talk about each of them. I don't even need an answer yet. I just want to know. What are we doing on number 1?
We're doing
Parker.
Multiplication counting principle.
Good.
Yes.
Multiplication counting principle. You have different choices. You plant an oak, hickory, and dogwood. You must choose among 9 varieties, 7 varieties of hickory, and 3 of dogwood. So you have your 9, your 7, and your 3. You get to choose. So it's 9 times 7 times 3. And that gives you your solution. All right? Versus number 5, and how many different ways can you line up 10 people? What are we doing there? Lee? We're doing factorials, not really permutations. The difference here is you have 10 spots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A good way to do these when you're struggling figuring it out is ask yourself, okay, I've got 10. How many people can I put here? Or how many things? Well, in the first spot, first in line, out of 10 people, how many people can I choose to go there? 10. How many can I choose to go in the second?
9.
Okay,
8.
and so on, right? So when we keep doing that, what does that end up being?
10 factorial.
That ends up being 10 factorial. So you end up with 10 factorial on that one. Once again, if you do that, that'll give you your solution.
Which is
Okay?
3,628,800.
So it's a lot.
Yeah.
All right, number 9. Of 28 projects being judged, the top 5 will receive rewards. What are we using there? How many different ways can you give those awards?
Permutations.
Yes, that's a permutation. I have 28. I want to pick. Notice I say pick there. That doesn't mean pick. It means permutation. But 28 pick 5. 28 pick 5 is, well, that's NPR, right? This is N, this is R, so that's 28.
Factorial over 23 factorial.
Good. 28 minus 5 factorial, or 28 factorial over 23 factorial, which I'm hoping that everyone realizes in this case that means I have 28 times 27 times 26 times 25 times 24. Notice I only have 5 slots. 5 projects are going to be judged. You could pick 28 for the first one, 27 for the second, 26, 25, and 24. That's what, when you put this into your calculator, you could actually, that's what your calculator does. So how do you put it into your calculator? Well, first thing you want to do, let's go ahead and put 28 in. The N. And then want you to go to math and go over to PRB again.
1 second, let me write this in my notes.
Okay, so we put in the N, we go to math, and then we go down to number 2, which is NPR. And we put in the 5 next, and we hit enter. That's our solution. That's a lot of ways, dude, that you can get 5. You're lucky you don't have to do some kind of visual diagram for that. Okay?
11,700.
Okay. Your assignment today, mixed side. I want you to do 1 through 10 on top. Cross these out.
Can we do it on a separate sheet or on the?
You can do it there. That's fine. And then 21 through 32.
Oh, that's the rest of it.
Yep. That's the rest of it. Remember, there are 3 different ways you might have there. Yep.
So there's not too many